All right, hello everybody. I assume that if you're watching this video, you are likely from the PHYS 232 course at UBC Okanagan. And so we're obviously in a situation here where we're transitioning from a traditional face-to-face style of lecture to something that's exclusively online. And so we certainly are in a unique situation here, and so I'm going to do my best to develop a system where I can create the course content and deliver it to you in a reasonable way. Um, Obviously, this is being done with essentially no preparation and really no outside support. So I hope that this goes smoothly, and I hope that you'll be patient with me as I try to work out a system that is going to be effective for us. So I will be sending out an email explaining details of how the remainder of the course will run, and I'll also post those details to the course website. However, what I'd like to do with these videos is to try to focus primarily exclusively on the physics. people.oak.ubc.ca/J Bobowski phys 232.html. And so I do encourage you to check the course website for updates and try to check regularly, and we'll take it from there. So, without further ado, I think what we should do is to just quickly review what we've been thinking about lately. What we've been trying to do is develop a method to fit data to a function that was of the form some coefficients ak times some functions of x. And we could have as many terms in the sum as we want, let's say m terms. And what we're trying to do is we're trying to fit this to a set of measurements to determine the best fit values of all m of the ak parameters. And we found that we could do that. And the way we did it was we minimized chi-squared, and we found that we could express the minimization of chi-squared as a pretty convenient matrix equation. It was a column matrix beta times a square matrix alpha, and then another column matrix A. The A column matrix contains all of the parameters that we're trying to determine. So all of these unknown coefficients, A1 to AM. And if this matrix equation is actually correct, it makes solving the problem actually pretty easy, because all we have to do is invert alpha and multiply both sides of the equation by alpha inverse to isolate the column matrix of our unknown parameters, and then we find that A is just alpha inverse times beta, and we ended up calling this alpha inverse matrix the error matrix epsilon. Okay, and what was really convenient about this, and what I want to emphasize the most in order to motivate the next topic, is that there's absolutely no guesswork involved in determining the best fit values for the A parameters. That is, we can exactly determine alpha and beta, and then calculate the inverse of alpha in software, and therefore determine A without any guesswork. So in particular, if we had measured the data set x versus y plus or minus sigma for, say, I equals 1 to n, then it turned out that we could calculate the elements of the beta matrix exactly. So say the alpha element of beta was equal to the sum of I equals 1 to n of 1 over sigma squared yi fl of xi. Okay, and if we have a fit function where we know all of the functions of f, all of the FLs, and we've measured x, and we've measured y, and we know the error in y, then we can just evaluate the sum and we can calculate every element of beta without any trouble. The elements of alpha require two indices because we need a row number and a column number. But it was likewise easy to calculate all of the alpha elements. It was 1 over sigma squared FL of x and times FK of x. So again, in fact, alpha doesn't have any y dependence at all, but if we know the functions f and we know x values and sigma values, then we just evaluate the sum and we can calculate every single element of alpha. Then we invert it to get the error matrix, and error matrix times beta tells us our best fit parameters. So the point that I want to emphasize the most is that there is no guesswork required to determine the best fit values of alpha k. In other words, they're exactly determined from the measurements x and y plus or minus sigma. Okay, so sometimes a function that we want to fit our data to can't be written in the form of y is a times a function of x, say a1 times a function of x plus a2 times another function of x plus a3 times another function of x, and so on. Sometimes our functions are going to be explicitly nonlinear, and so that's what we want to talk about now. Nonlinear fits. And we're going to start this by way of an example. And so the example that we're going to work with is a simple one. We're just going to say y is equal to a1 times sine of a2x. So this is clearly not of the form, say, of a1 f1x plus a2 f2x, right? And the reason it's not of that form is because the a2 parameter is inside the argument of the sine function, and so we can't separate that a2 as some coefficient times a function of x. So what I'd like to try to do is to construct a table where we try to take this nonlinear function and do the same types of manipulations we did when we were working out the best fit for, say, a straight line function. And I want to see where things start to break down. So I want to compare / contrast linear fit. And so let's just use a straight line. a1 plus a2 times x to the nonlinear fit, and we'll use this a1 times sine of a2x. And so we'll do this by constructing a table. And so let's see if we can make this work. So on one side of the table, we'll have our linear fit, and on the other side, we'll have our nonlinear fit. So y is a1 plus a2x, and y is a1 sine a2x. All right, so if we think back to how we did our linear fits, the first thing we did is we wrote down chi-squared. So chi-squared was the sum of I equals 1 to n. And what we had to do is we had to take the deviation between the measured data point and the calculated value based on the fit function. We divided that by the uncertainty. And so in some sense, the sum is weighted by the size of the uncertainty. And the whole thing was squared. Okay. And so for our nonlinear fit, let's just try to do the same thing. So I'm just going to write down exactly the same thing. Chi-squared is the measured value subtracted from the calculated value, divide by the uncertainty, and then square the whole thing. Okay, and so we want to minimize this chi-squared. So let's just substitute in the expression for our fit function. So on the linear side, we're going to have yi minus, so a straight line, so minus an intercept a1, and then minus a slope a2 times x. And then we divide by sigma squared. Okay, so on the nonlinear side, we do the same thing. So the only difference is, of course, our function is now an a1 sine a2 xi divided by sigma I and squared. Okay, so remember where chi-squared came from. This was inside the argument of an exponential when we were trying to calculate the probability that we would measure a data set x1 and y1 and then x2 and y2 and so on. And what we were doing is we were doing this method of maximum likelihood, and we maximized the probability by minimizing the chi-squared. The chi-squared was in an exponential with a minus sign, so if we make that as small as possible, then we maximize the probability. It makes sense, right? We're calculating a deviation between the measured and calculated data points, and a good fit would have as small possible deviation over all of the measured values from I equals 1 to n. Okay, so the types of things we had to do is we had to minimize chi-squared by taking its derivative with respect to, say, a1 and setting that equal to 0. And then we would do the same thing for a2, but let's start with a1. So let's see, when we take the derivative, we get a factor of 2, and then the sum, and then we're going to have yi minus a1 minus a2 xi over sigma I. And then we have to take the derivative of what's inside, and we have a term that's minus a1 over sigma I, and so when we take the a1 derivative, we pick up a minus 1 over sigma I. Okay, and then to do the minimization, we set that equal to 0. Okay, the 2 out front doesn't matter, right? We can divide by 2. 0 divided by 2 is still 0. And what was convenient about this is we could separate this into terms on, say, the left-hand side that involved, say, yi values. And then on the right-hand side, we could have terms that don't have y's in them. So, for example, we have a yi over sigma I, and we get it squared, right? Because we have a sigma I and a sigma I over here. Okay, there's also a minus sign, so let's suppose we take this over to the other side where we had the 0, and we get rid of the minus sign. And then what's left over is the minus sign from the 1 over sigma, and the minus signs in front of the a1 and the a2 will cancel, and so we would get the sum of a1 plus a2 xi over sigma I squared. All right, I'm going to call this equation 1, and we'll come back to it. Let's scroll up just a little bit. And what I want to really emphasize here is that on the left-hand side of equation 1, there is no a1 or a2. Okay, so now let's go back to the nonlinear fit, and we want to do the same sort of thing. And so we're going to calculate the derivative of chi-squared with respect to a1. All right, and so we're going to get the same factor of 2, the sum of yi minus a1 sine a2xi divided by sigma I. And, okay, then we're going to times. So we're going to take the derivative of what's inside. And so we have a term that is minus a1 sine a2xi over sigma I. And when we take the a1 derivative, what we would be left with is the minus sine a2xi over sigma I. And then that would have to be equal to 0. All right. We could try to do the same thing we did for the linear fits. We can take the yi and move it over to the left side. But this time, if we look at yi, it's going to multiply minus sine a2xi over sigma. And so when we move that over to the other side of the equation, what we end up with is, let's see, it's a yi sine a2xi, and then we have a sigma in both factors, and so we get a sigma I squared. Okay, and then that's equal to everything that's left over, and sorry, let's go back down. What's left over? We have the a1. So we have an a1 over sigma and a sine a2, and then we have to multiply that by a sine a2 over sigma, so we're going to get sine squared over sigma squared. Okay, so that's equal to sum of I, and we're going to get an a1, ai, sorry, not ai, it's a1. a1, and we'll get sine squared a2xi over sigma I squared. So this is the equivalent of equation 1 for our nonlinear fit, so I'm going to call this, say, equation 1 prime. But let's just point out that whereas over here we had no a's on the left-hand side, we have an a2 on the left-hand side. So that's one of the difference. One of our fit parameters is on the left-hand side of the equation. Okay. Anyways, we forge on, and what we're going to have to do is we're going to have to do the same thing for a2. And so let's go back to the linear fit. So now we're going to take this derivative with respect to a2. And if we just go take a peek at what chi-squared was, The only difference between the a1 and the a2 derivative is that the a2 multiplies an xi. Okay, otherwise it's the same. So when we do the derivative, what we end up getting is 2 times the sum of yi minus a1 minus a2 xi over sigma I multiplied by, before we just had 1 over sigma, but this time our a2 multiplies an x. Okay, so we have an x over sigma with a minus sign, and then that has to be equal to 0. Okay, so we end up doing the same kind of separation of terms that we did last time. We're going to take whatever has the y in it and move it over to the other side. So this time we get a yi times an xi. So on the left-hand side, what we'll end up with is the sum of, let's see, xi yi over sigma I squared. And what remains is a sum of xi over sigma I squared, and then we have a1 plus a2 xi, and I think that's it. Okay, we're going to call this equation 2. That's our derivative with respect to a2. And then again, on the left-hand side of the equation, we have no a1 or a2. Okay, and we want to do the same thing. If I want to minimize chi-squared with respect to my fit parameters, I have to take the derivative with respect to a2 and set that equal to 0. And so we scroll way back, and we see that when we take the a2 derivative of chi-squared, it's going to be a little bit complicated because we have a sine a2 times x. And so when we take the a2 derivative, we're going to end up having to do chain rule, where the sine is going to become a cos, and then we take the derivative of the a2xi inside, and we'll get a factor of x, and it's going to be a little bit messy. But nevertheless, we can just go ahead and try to do that. So when we take the derivative, we'll get our usual factor of 2. Oh, sorry. Let's see if I can get this back. Oh. Okay, here we go. So we take the a2 derivative, we'll get our usual factor of 2, and then we'd have the sum, and what's inside was yi minus a1 sine a2xi. We divide by sigma I, and then all of that would have to be multiplied by, so let's see, we have a minus a1. When we do the a2 derivative, like we talked about, an xi is going to come out, and then, here, let me scroll over and give myself a bit more room. The sine becomes a cos, so we're going to get cos of a2xi, and then we have to divide by sigma I, and then we have to set that all equal to 0. So when we try to move the yi term to the other side, what we get is we get a whole bunch of other stuff that multiplies it. We have this a1, x1, cos a2. So if we tried to do that on the left-hand side, we'd have this yi xi a1 cos a2 xi. There's two factors of 1 over sigma, so we get sigma squared. And what's going to be left on the other side is a product of the sine and the cosine terms. In fact, there's going to be an a1 squared. There'll be a sum, won't there? A1 squared. There's an xi, and there's a sine a2. And there's a cos a2xi, and then that gets divided by sigma I squared. And so this thing is a disaster. This is going to be equation 2 prime, and it's looking pretty hopeless. So this does involve a1 and a2. So that's in part one of the important distinctions between the linear fit and the nonlinear fit cases. Okay. What was nice is that we could take equations 1 and 2 for the linear fit case, and we can express these as, what happened here? My equation 1 got a little bit messed up, it looks like. So that was going to be an xi, right? Okay, so if we take equations 1 and 2, we could express those as a pretty simple little matrix equation. And in particular, we could write for the linear fit case, we can express equations 1 and 2 as a matrix. That is, we could write down a single equation that contains both 1 and 2. And what that looked like is that for the the left-hand side of equation 1, we had yi over sigma I squared. And for the left-hand side of equation 2, you can see it at the top of the screen, we get an xi yi over sigma I squared. And so that's the left-hand side of equations 1 and 2. For the right-hand side, if we construct a square matrix that has the elements of, well, let's go back to equation 1, and let's look at the coefficient of a1. So yeah, I don't know what happened. My equation 1 got a little messed up here, so let's see if we can fix that. So this was going to be a2, and this was going to be sigma I squared. Okay, what's the coefficient of a1? It's 1 over sigma I squared. While we're here, let's look at the coefficient of a2. It's xi over sigma I squared. And so in our square matrix, the coefficient of a1 I'm going to enter as 1 over sigma I squared. And for a2, we had xi over sigma I squared. So we have equation 2 up here at the top. The coefficient of a1 is xi over sigma I squared. And so I'm going to enter that over here, xi over sigma I squared. And the coefficient of a2 is xi times xi over sigma I squared, or it's xi squared over sigma I squared. And if we then write a1, a2, if you just did this matrix multiplication, the square matrix times the A column matrix, you would reproduce exactly equations 1 and 2. And this is, in fact, this is our beta column matrix, this is our square alpha matrix, and this is our matrix of fit parameters. And so clearly the solution for A1 is, for the A column matrix is just alpha inverse times beta. And so that's exactly everything we did for our linear fits. And in fact, it can be generalized to not just an intercept and a slope, but any function of the form of this sum of ak times fk of x. Okay, one of the really beautiful things about this is that what we found out was that if we really examine the properties of alpha inverse, which we called the error matrix epsilon, we found that the diagonal elements of epsilon gave the uncertainties in our parameters. And so, like I said, everything in beta and everything in alpha we could calculate exactly. And so there's no guesswork in finding the best fit parameters. Now, if we go back and look at equations A1 prime and A2 prime, you can see that it's completely hopeless to write these two equations as a matrix where we have on the left-hand side something that involves just y and x, no a's, right? That's the important thing. There's no A1 or A2. And so in equations 1 prime and 2 prime, we just don't have that situation. We have y times A2, or the sine of A2, and we have y times A1 times the cosine of A2. It's just a complete mess. And so it's completely hopeless to write an equivalent expression, or let's say an equivalent matrix equation, an equivalent matrix equation for the nonlinear fit. In other words, we cannot isolate the A1 and A2 parameters. Okay, so what that means is we need to develop an alternative way to evaluate when chi-squared is minimized. What set of parameters A1 and A2 actually result in the minimum of chi-squared? So we need to develop an alternative fitting method for nonlinear functions. And keep in mind, what we started with is a pretty basic nonlinear function. It was just the coefficient A1 times sine of A2x, and that already became a really hopeless case. And so if you had an even more complicated function, then it just gets worse. So to start, what we're going to do is we're really going to think about trying to do this in the simplest possible way. So the objective is still to minimize chi-squared. Okay, so chi-squared, once again, is the sum of the square of the deviations weighted by the uncertainty in y. Okay, and let's just stick with our example of the sine function. So I want to put in our sine function. So it was a1 sine a2xi over sigma I squared. So the question is really, what values, or let's say what set of a1, a2 values result in the minimum chi-squared. Okay, and as I said, what we're going to do is we're going to do the most simple-minded thing possible. And the strategy is simply to, in words, what we're going to do is we're just going to pick a whole bunch of different a1, a2 values, and we're just going to evaluate what chi-squared comes out to be, and we'll make a big table, and then we'll search through the table and figure out when is chi-squared the smallest possible number. So what we could do is we could pick a range of possible values for a1 and a2. So what that might look like is we're going to say a1 can't possibly be less than some a1 minimum, and it can't be greater than some a1 max. Likewise, there's some minimum possible value for a2, and there's a maximum possible value for a2. So already that's different than the linear fit case, right? Because in the linear fit case, we never had to say anything about what the possibilities for our fit parameters were. We just extracted values based on the measured data and the model. So in order to do this, we have to know something about our model and the physical system. And so there might have to be some thought about what the appropriate range of values for each parameter might be. And so maybe what we'll do is we'll come back to that point in just a second. Let's first fully develop the strategy. So step 2 is then to say, well, we're going to pick a step size. So we pick a step size. We'll have to pick a step size for each parameter, delta A1 and delta A2. And you could probably guess what we're going to do is we're going to evaluate chi-squared at every possible combination of A1 and A2, starting from A1 min and increasing in steps of delta A1 up to A1 max, and likewise for A2 min, increasing in steps of delta A2 all the way to A2 max. So a small delta A1 and delta A2 is good because we're going to get high resolution. but it is computationally expensive. So we're going to have to calculate chi-squared many times if we have very small step sizes. Okay, so step 3 is to evaluate chi-squared at all possible combinations of A1, A2. And then the best fit parameters are the pair of, let's say there's some special pair A1 star and A2 star that give the minimum chi-squared. We can attempt to express this condition in a figure, and so this is maybe going to challenge my artistic ability, but let's see if we can pull it off. So I'm going to try to draw a 3D plot. On the vertical axis are going to be the chi-squared values, and then we'll have one axis that corresponds to A1 and one axis that corresponds to A2. And so there's this horizontal plane, the A1, A2 plane, which is like our parameter space. And we're going to explore that parameter space and see how chi-squared varies as we move around in that space. And we're looking for a minimum. And so I'm going to try to draw a surface. And so there's the surface that has kind of a structure that dips down, and so there's some curvature to that surface, and what happens is that there's a little well that dips down, and what we can imagine is that we can take this down into our, let's see if I can clean up my picture a little bit. So there's this well with some curvature. And we can take that down into our A1, A2 plane, and we could find A2 star and A1 star that locate this minimum. And so right here is the point that is the minimum chi-squared value. So minimum of chi-squared. And then of course if you really want to find that minimum, what you need is very finely spaced calculations of chi-squared. So that's what we were talking about with the small delta A1 and delta A2 values. Okay, so what we're going to do next time is we're going to try to think about how we might estimate the uncertainties in these parameter values. But before we stop today, what I want to do is I just want to go back and think about this point that we made up here where we said, you know, what we had to do is we had to pick a range of values. And in order to pick a reasonable range of values, we need to know something about our model and our physical system. So for example, if we picked a range of values that did not contain A1 star and A2 star, then we have no chance of finding the true minimum. Okay. So let's return to the point about having to be knowledgeable about our model and system in order to pick suitable as you can see, I'm still getting used to this. Okay, here we go. In order to pick suitable ranges for our parameters. You know, besides just missing the location of the minimum, you also might pick an extremely wide range of parameters. And in that case, what you're going to have to do is you're going to have to calculate an enormous number of chi-squared values, and so that's very inefficient. So I want to think about this point by way of an example. Fitting a Lorentzian. So if you think back to Physics 231, we had this LRC circuit. So this might be, say, the voltage across a resistor in an LRC circuit. So that circuit looked like what we had is a function generator and an inductor and a capacitor and then a resistor. And so if this is L, C, and R, what we might be doing is measuring the voltage across the resistor as a function of the frequency of the generator voltage. So we might be tuning the frequency if we're looking at the frequency response. Another example is if you did the root card experiment in this course in 232, then the second day you had a little solenoid and a magnetic piston, and you changed the frequency of the current in the solenoid and looked at how the amplitude of the oscillations of the piston changed. And again, that is also a model that is Lorentzian-like, or it is a Lorentzian. Okay, and so what does the model look like? Let's just be general. Y might be the amplitude of the voltage across the resistor or something like that. So the model is some coefficient A plus divided by the square root of 1 plus frequency squared over this parameter gamma squared, and then it's 1 minus omega naught squared over omega squared, and then all of that was squared. And so if we're trying to do a nonlinear fit, what we might be trying to extract is the following. So let's suppose that you measured y plus or minus sigma versus omega. Then you want to determine the parameters, which could be A, this gamma quantity and omega naught. So it's 3 parameters. And that's clearly a nonlinear function. And so we're going to need to use this strategy that we talked about where we're going to pick ranges for all of our parameters. And now, we drew a plot of parameter space in the example above. And so we had a parameter A1 and an A2, and on the vertical axis we had chi-squared. So we could imagine doing something like that, but we couldn't even draw the picture, okay, because we'd need 3 axes for our parameters and then a 4th axis for chi-squared. Okay, so the question is, how should we select the ranges for each parameter? And the answer is we should look at the measured data and estimate values for each parameter. Okay, so if we took the measured data and we made a plot of y versus omega, the frequency, what it might look like is something like this. And we want to begin to try to understand what each of the parameters in our model represents. And so when we look at the data, we see it's a peaked function. So there's a resonance. And so we might ask, well, at what value of the frequency is this function y of omega a maximum? Well, we have a constant divided by some stuff. It's 1 plus some stuff. If we could make that stuff after the 1 equal to 0, then we're going to divide by the smallest possible number, because all the stuff that comes after the 1 has to be positive because they're all squared quantities. So if we set our frequency omega equal to omega naught, then in here we have a 1 minus omega naught over omega naught, which is going to be 1 minus 1, which is 0. So it must be the case that our function peaks when frequency is equal to omega naught. In other words, we could estimate omega naught by looking at the frequency where the measured data is a maximum. So omega naught is estimated by finding the frequency at which y is a max. Okay, so there's something where we can use our knowledge about our model and the measured data to estimate one of our parameters. And so we go back to this model here and we say, okay, let's say omega is equal to omega naught, then y is equal to a divided by the square root of 1, which is just a. So what a represents is the maximum value of y. A is estimated by looking at the peak value of the measured y data. And so you can see we don't want to go into our fit blind. We want to have some expectation of what our best fit parameters ought to be. The estimate of gamma is a little less trivial, but it turns out that if we were to set frequency equal to omega naught plus or minus gamma, then if you examined the model, you would find that y would be equal to a over the square root of 2. Okay, so then we come back and we say, if omega is equal to omega naught plus or minus, I said gamma, it's gamma divided by 2. Oh, shoot, sorry. Then y is equal to a over root 2. So what we could do is we could say, let's find on our plot the height, a over root 2, and then if we extrapolate back down to the frequency axis, we would say that this is omega naught minus gamma over 2, and this is omega naught plus gamma over 2. And in other words, this width here is gamma. The width of our function when we're at the peak value divided by root 2 is an estimate of gamma. So gamma is estimated by finding the width of the measured data, the width and frequency of the measured data when y is equal to the peak value a over root 2. And so that one's less obvious, but this really accentuates the point that when you're coming to do these fits, you really want to have a good understanding of the model and what the parameters mean and the physics of your problem. Okay, so with that, I think that's where I'm going to stop for today. Hopefully this went relatively smooth, and we'll try to continue with this and see if we can power through till the end of the term. All right, thank you very much.